Today we're going to learn how to solve problems using linear programming. Well, you might be wondering what exactly is linear programming, and I thought it might be nice to kind of jump down in our notes to an example problem so you can get an idea of why we're going to use this new method to solve this problem. Each week, Mackenzie can make 10 to 25 necklaces and 15 to 40 pairs of earrings. She earns profits of $3 on each pair of earrings and $5 on each necklace, and she plans to sell at least 30 pieces of jewelry. How can she maximize her profit? So there's a lot happening here. We're going to have many different constraints, even more so than we did in step 7. And there's a component of maximizing profit. That's the big difference here. We're trying to maximize her profit. We're trying to look at all these constraints and say, okay, which combination is going to give her the best chance of making the most money? There are going to be some steps that we're going to follow, and those are down here at the bottom of your notes. But before we do that, we're going to start with some easier problems at the beginning of our notes, where they have already written out a system of inequalities and they've already done a lot of the work for us. So all we're going to have to do is optimize it, or take all of the vertices of our region that we've created from these constraints and figure out which vertex creates the best profit. Let's go back to the beginning of our notes. Again, linear programming is simply a method for finding the maximum or the minimum value, depending on your situation, of a function for a given system of inequalities. We know from step 7 that we can graph multiple inequalities on the same graph in shade and get a region. In fact, in the last step, we practiced finding the coordinates of these 3 vertices when we had a triangular region. Each one of these inequalities is a constraint. It's a limitation about the situation. Like in our problem, Mackenzie can only make so many necklaces and so many pairs of earrings. She has to sleep. She can't work around the clock making necklaces and earrings. This region is going to be called our feasible region. Sometimes the feasible region won't be completely contained or bounded. Do you see how there's a vertex at the top and the top right, but then it goes on forever towards the bottom? That's an example of an unbounded region. All right, in the first example, the system of inequalities has already been created for us. It consists of these first 3 inequalities. This last piece right here at the end, that is going to be our profit function that we're trying to maximize or minimize. Notice it's f of, fix that a little bit, because I know it's hard to see now that I've highlighted it, f of x, y. It's a function notation that we're going to be using. So let's graph these. First, I'm going to graph the first constraint right here. I'm going to graph it in red so I remember which one's which. And this is a line at x equals 5. It's going to be greater than or equal to, so it's going to be a solid line. Have it. And where would I shade? I would shade left of this line. Notice I'm not doing a lot of shading. I'm just kind of getting a direction. When you have a lot of constraints on the same graph, sometimes the shading can get confusing. So I just want to kind of mark that it's going to be to the left side of that line. Let's do the next line. This line is the line y is less than or equal to 4. So I'm going to go up to 4 on my graph for y. 1, 2, 3, 4. Get the next line on our graph. Again, this is less than or equal to, so it will be a solid line. I don't have to make it dashed. And I am shading less than this line. Now, I don't need to shade on this side of my blue line. I only need to shade over here. I know because there's no shading on the right side of the line. I'm trying to find the common region. So I'm just going to kind of shade over here instead. In fact, I don't need the shading that's above my blue line from the red line anymore. I can get rid of that. I know that this is my common region so far, right in here. Now I have one more inequality to graph. I'm going to move x to the other side and graph y is greater than or equal to 2 minus x. That means I'm going to start at 2, and I'm going to go down one, right one, down one, right one. And then I'll connect them with a line. And again, this is a solid line. And where would it be shaded? It's going to be shaded above the green line, so this direction. Now, if you look at all of the shading, I've shaded left of the red line, below the blue line, and above the green line. It's going to make this triangular region right here. So I'm going to eliminate all my other shading. Oh, away my green line. I'm going to carefully eliminate my other shading to make this a little easier to see if I can without eliminating my green line. There we go. Oh, I got it again. That's much better. Okay, so my common region that I want to shade is right in here. This is my feasible region. That means that any point in this shaded gray region could solve my constraints. It will satisfy all three constraints. It will be less than 4 for y, it'll be less than 5 for x, and it will also, when I add the two coordinates together, they'd be greater than 2. Alright, so we found the feasible region, but now we need the coordinates of the feasible region. Alright, this coordinate right here is the point 1, 2, 3, 4, 5, 4. This point right down here is the point 5, negative 3. And finally, this point over here, my third vertex, is the point negative 2, 4. So the next thing that I want to do, I want to take these points, order doesn't matter, and I want to run them through my optimization function. F of xy equals 3x minus 2y. To get my answer, 3x minus 2y, 3x minus 2y, 3x minus 2y. I'm going to take out the x and I'm going to replace it with what x equals. I'm going to do that for each one. Take out x. Replace it with what x equals, and then I'll do the same with the y values. Take out y, and replace it with what y equals. In this case, it's 4, 4, and 3. And then I'll just compute. 3 times negative 2 is negative 6, minus 8 is negative 14. 15 minus 8 is 7. 15 minus 6 is 9. So for this function, the maximum value is going to be 9, and the minimum value is going to be negative 14. Let's try another one. We're going to graph these. This one's a little bit more complicated. We have 3 slanted lines that we have to graph, and then we will put it into our optimization function. We'll take the vertices and we will optimize. All right, the first one, I'm going to move x to the other side and divide by 2. So my inequality is y is less than or equal to 1 plus 1/2 x. So I'm going to start with 1, and I'm going to go up 1 over 2. And back 1, left 2, down 1, left 2. Take your time with this because you want your graph to be precise and neat. Connect them with a line. It is a solid line because it is less than or equal to. Alright, there's our first line. The next one, I'm going to subtract x from both sides to move my x over and divide by negative 2. So then I get y is greater than, remember we're dividing by a negative, so I have to flip my symbol, negative 2 plus 1/2 x. Also, before I graph this line, I'm going to give my red line some directionality. I'm shading less than the line, in other words, where 0, 0 satisfies the solution. So I would shade down. And again, I'm not doing a lot of shading because I just want to get an idea. Otherwise, the shading can make things look complicated. For the blue line, I'm going to begin at negative 2. And again, I'm going up 1, right 2. Over and over, across my graph. Down 1, back 2. Across the graph. I'm going to connect them with a line. And this one I'm going to shade above the blue line because it is greater than or equal to. A solid line. And I'm shading above the blue line. So right now, it's just the region in between these lines. Let's grab our third inequality. If I subtract x from both sides, I have y is greater than or equal to negative 2 minus x. So I'll start at negative 2, and I will go down 1, right 1, or up 1, left 1, across my graph, and then I'll grab my shape, my line, and connect my points. Shading for this line, we're shading above the green line. Y, if I put a 0 in, is greater than negative 2 minus 0, so I'm shading this direction. So all in all, my shading is this region. Notice that it goes on forever. Because I only have these three constraints, my shaded region is strictly going to go on forever. It's going to be an unbounded region. So when I try to find my vertices, I'm not going to have as many as I did in the first one. I have one here and one here. This is the vertex 0, -2, and this is the vertex -2, 0. So I only have these 2 points to put through my function. F of xy is 2x plus 3y. 2 times x plus 3 times y. 2 times x plus 3 times y. This gives me -4. This gives me -6. This would be my maximum. This would be my minimum. Now we need to be careful here in letting this be our final answer. For instance, I'm going to pick another point in my region. I'm going to pick the point 3, 1 right here. That's the point 3, 1. It's not a vertex, but it's still another point in the solution. If I run that point through this function, 2 times 3 is 6, plus 3 times 1 is 3. 6 plus 3 is 9. 9 is bigger than what we thought was the max. So when you're doing this, you're going to find a max and a min from your table, but then you need to pick another point and see if it eliminates one of your answers. So for this problem, we will have a minimum at this vertex, but we will not have a maximum because we could always find another point that keeps beating out the previous record for the maximum. Alright, so let's take a look at this entire problem from the start. The first thing we want to do according to our steps is define the variables. So in this problem, we're dealing with E for number of earrings, and N for number of necklaces. We've defined our variables. Next step, we want to write a system of inequalities from the word problem. The first sentence says, each week Mackenzie can make 10 to 20 necklaces. 10 to 20 necklaces. When it's between, we can put our variable between the two numbers. She can make 10, she can make 25, and everything in between. And 15 to 40 pairs of earrings. 15 to 40 earrings, including 15 and 40. Now the next part here, we're talking about profit. Talking about profit. Anytime we get into the money portion, that's going to go into our profit function. F of xy, well in this case we're not using x and y, f of en, we make $3 on each pair of earrings and $5 on each necklace. So that's where that information is going to go. And then finally, we have one other little bit of information here. She plans to sell at least 30 pieces of jewelry. What does that mean? That means if you take the number of earrings and the number of necklaces, it's going to be greater than or equal to 30. So let's see what this looks like on our graph. When I graph n between 10 and 25, there's 10, 25, let's see, 22, 24, 26, 28. So 25 would be right here in the middle. And it's shaded in between. It's shaded above 10 but below 25. Now we'll do the same with the earrings. We have one at 15, 12, 14, 15 would be right here. Normally I would use my shape tool, however I'm trying to keep your video concise. Sometimes getting my lines to line up nicely on the computer, I'm just trying to draw them freehand as nicely as I can. Again, it's in between these blue lines because E is in between 15 and 40, greater than 15, less than 40. So far my region would just be this box right here in the center. But I have one more line to graph. I want to get N by itself because that's where my y-axis would normally be. To do that, I'm going to subtract E from both sides. Actually, you know what? Let's back up. Let's not do it that way because we could simply just use our intercepts. When E is 0, when I don't sell any earrings, I would sell 30 necklaces. And when I don't sell any necklaces, 0, E is 30. So I will just connect them right here. Again, it's greater than this green line. So where would the numbers be greater than? It would be above this green line, not this tiny triangle, but above this line. So my feasible region ends up being right here. It's kind of like the box with a little corner chopped off. And this is my entire feasible region. Now I'm going to end up with 1, 2, 3, 4, 5 vertices. I'm going to start right here. This is the vertex 40, 10. This is the vertex 40, 25. This is the vertex 15, 25. These vertices are going to be a little bit harder to figure out, but I know that this is the intersection of my green equation and parts of my red equation. Right here, this is where N is 10. N is 10. I do know that because it's on the red line. So I know it's something 10. So if I put a 10 in my green equation here, what is E? E would be 20. 20 plus 10 makes 30. Similarly, right here, I know this is part of the blue line. The blue line is E equals 15. So going back into my green equation again with E equals to 15. 15 plus what is 30? N would also be 15. So I found all 5 of my vertices. Now I'm going to put them through my profit function. 15, 15, 20, 10, 40, 10, 40, 25, 15, 25. There's the 5 vertices. My function again is 3e plus 5n. So I'm taking 3 times 15 plus 5 times 15. 3 times 20 plus 5 times 10. 3 times 40 plus 5 times 10. 3 times 40 plus 5 times 25. 3 times 15 plus 5 times 25. Alright, this gives me 45 plus 75, which is 120. She would make $120 if she did it that way. Let's just double check that on the calculator. 45 plus 15 times 5 is 75, is 120. This would be 60 plus 50, which is 110. 120 plus 50 is 170. 120 plus 125. Or write it out if you need, if you don't feel like using your calculator. That gives us 245. 45 plus 125 gives us 170. So, how can she maximize her profit? We don't actually care what the minimum value is here. We just want to know her maximum. So we would say that if she makes and sells 40 earrings and 25 necklaces, she will make a maximum profit of $245.